So hello and guten Tag. To begin, I want to thank the organizers of this event. Vielen Dank. And I think that some years after, this event will be mentioned in books of history. Now to my presentation. My report is the first one in the series of 3 reports from our group from Russia. They are united by a common theme, which is xenon. Xenon is a noble gas, and our reports are related to use of xenon for cryoprotection. The use of xenon for cryoprotection was first proposed by Robert Prigoda, American chemist, who proposed it as long ago as in 1969. He suggested that in the presence of xenon, water would form crystals of cryonics hydrate instead of that of ice. He didn't motivate why he thought that crystals of hydrate are better than crystals of ice, but still he thought that it would work somehow. Since that time, there have been scattered reports upon cryoprotective properties of xenon. Some of them are listed in this presentation at the references slide at the end of the presentation. Others are in form of private communications, not published because of not very conclusive results. One of these works that should be mentioned is work by a group of Vladimir Kovanov in Russia. Vladimir Kovanov was a prominent surgeon in Russia, author of textbooks on surgery, and in the late years of his life, he and his group worked on use of xenon for cryoprotection. They pretend that they could store a rat for 3 hours in liquid nitrogen. Then they warmed it and transplanted its heart to another rat, and it resumed heart beating. But this I've never heard about anybody who could confirm these results after that. So anyone can read this text. It is translated from Russian patent to English, but the translation is awful, so I recommend you to read Russian original. It is listed in the references. Xenon is somewhat a mystical substance. You know, it is chemically inert because it's a noble gas. But it has some prominent physiological impacts. Well, it's absolutely non-toxic. It's understandable since it's inert, but it has some actions such as an anesthetic action. It is maybe the best anesthetic known today. It is routinely used in some clinics in Germany and in Russia as anesthetic. And the only drawback of it is that it is not so cheap. It has a very high price. And you can see that there are some other properties that look interesting from the point of cryoprotection, and the nature of these abilities are still unknown. So it's a mystical substance. Of course, there are certain hypotheses on that. but none of these hypotheses is generally accepted. If we compare xenon with common cryoprotectants that are used today, you can see that if xenon is really a cryoprotectant, then it can beat any other cryoprotectant on all the points. And of course, the main drawback of today's cryoprotectants is their toxicity in concentrations necessary to effect. So we have to answer three questions. Does xenon really act as a cryoprotectant? If yes, then what are the mechanisms? And if we know the mechanisms, then how we can apply them to cryopreservation, especially for cryopreservation of bulk biological objects, such as organs for transplantation, or head, or brain, or full body. To speak about the first question, we can definitely answer that xenon really acts as a cryoprotectant. You can find some references at the end. It looks that xenon is not a very powerful cryoprotectant compared to DMSO or glycerol or others. Or maybe it was not used in the right way. Maybe we need to change the protocols of its usage so it produces enough cryoprotection. So we have to understand what are the mechanisms of its cryoprotective actions. We can propose at least four possible mechanisms of cryoprotection. The first of them is accumulation of xenon in hydrophobic compartments of the cell, such as cell membranes and hydrophobic pockets in the protein molecules, so that it maintains membrane elasticity or fluidity and prevents proteins from deterioration. The next mechanism is formation of xenon hydrate crystals. That is what Prihoda proposed, that compete with ice for water molecules, and that are for some reason less destructive for cells and tissues. For example, they can be finer in size and or have less damaging shape. You know that ice crystals are needle-like, and xenon crystals may be, say, grain-like. The third option, the third mechanism is ice-blocking effect due to accumulation in the ice-water interface zone. And the fourth possible mechanism is vitrification of xenon water solution that may occur under different conditions than in case of pristine water. As for the first mechanism, there is work by Bucher and Sam that they modeled interaction of xenon with cellular membranes, and they showed that it accumulates in the core or in the lipid core of the membranes, and that it does diminish the temperature of liquid crystal to gel phase transition in membranes, and that it does improve fluidity of the membranes. So at least the first mechanisms of cryoprotection can be marked as probable. Now to the second mechanism and others. We concentrated on the mechanisms 2, 3, and 4. in this list. In order to understand them, we made some modeling, simulation of molecular dynamics of systems containing water and xenon, and containing water, ice, and xenon. These results are published in the Journal of Chemical Physics, but it is a journal on chemical physics, not on cryobiology. So this paper is focused on physical and chemical aspects of this study. Now I will not repeat all details that were published in this book, and I'll concentrate upon the cryobiological aspects of the study. Some computational details upon this work is that we used rather much water. It took to use a supercomputer to model it, and from 1 to 5% of xenon in the solution. Such high concentration may seem unrealistic because xenon is poorly soluble in water. But if we extrapolate the known dependency of solubility of xenon in water to temperatures below zero, then we say that it can be rather high. And we estimate the pressures necessary to obtain such concentrations of 1 to 3% as several tenths of bars. That is absolutely technically feasible. We made rather many runs of simulations for different concentrations and different temperatures. Take note on this corner, which is marked with such a blue-green color. I'll return to it. You can see that we had to count for the longer time, the lower is the temperature. And in the lowest temperature we studied, that is 250 degrees Kelvin, we couldn't end our studies because the system was equilibrating too slow. And even after counting for several hours on supercomputer, we couldn't reach the stabilization of the system. In fact, it looked like all the processes stopped and no diffusion was observed. Many results are that xenon in water, at these temperatures at least, it is surrounded by a solvation shell. You can see that this peak at 4 angstroms, it refers to the shell of water molecules bound to xenon atom. Xenon is inert, but molecules around xenon atom form, it should be a movie. For some reason, I cannot show you this video clip, but if you give me, yes.
Okay, no, it's not in full screen.
Okay. You can see that water molecules form more or less stable shell around the atom of xenon, so they are bound to it not with chemical bonds with xenon, but with hydrogen bonds between themselves. The lower the temperature, the more ordered is the shell. And it is not stable in the sense that molecules come and go, but when some molecule goes from the shell, then soon after that another molecule comes and takes its place. I know. Oh, wait a second. Some technical problems. Yes. When the concentration of xenon in water is high enough and temperature is low enough, then xenon shells form a crystal hydrate. You can see that crystal hydrate consists of water lattice. This lattice is more energetically beneficial than that of ice, so it's preferable by water, but it is not robust. And the xenon atoms in the cavities of the lattice, they stabilize the water, stabilize the crystal, and it can exist as a more or less a stable form of matter. And if we return a few slides back, yes, you can see those runs that are marked with green color. They are those where we observed formation of crystal hydrate. Not just formation, but homogeneous nucleation, which is much more exotic than formation itself. Here is again the movie. It doesn't move. Oh, it moves. You can see we managed to paint some atoms of xenon with green color. It was not so easy. Those that are green are in crystals. Those that are blue are in liquid water, and you see the formation of nucleation of the crystals. If you look from the beginning, you can see two attempts to nucleate, but then this nucleus is dissolved. And now you see two microcrystals that have successfully nucleated, and they are now growing. Now, I'll try to it's impossible. What? Here is the final stage. You can see two microcrystals, and it is obvious that they are crystals. As for the second possible mechanism of cryoprotective action, we can mark it as probable, at least at high enough concentrations of xenon. But it looks that the experiments in which cryoprotective ability of xenon was shown, that mechanism could not be applied because the pressures and concentrations were not high enough for it. But it looks like it is probable. The third mechanism. we simulated some systems containing of water with xenon dissolved and ice, and studied the conditions at which ice crystals melted or were growing. We have observed some very interesting effects, maybe not related to cryobiology. For example, we have observed that interface layer between ice and water in presence of xenon is more loose than in case of pristine water. That xenon atoms can penetrate ice for as much as 2 crystal layers, but they are expelled from it later in the process of crystal growth. And we found that xenon forms certain layers. You can see the xenon concentration is in red color. Layers in the water near the xenon surface, near the ice surface, with concentrations up to twice that of concentrations in the bulk water. But we couldn't see any effect of presence of xenon upon growth or melting of crystals. In the rate of both of them was independent of the presence of xenon. So we have to mark the third possible mechanism as unlikely. Also, some questions stay. And now to the most intriguing of all, the possibility of vitrification of water xenon solution. In a vitreous state, the diffusion coefficients are close to zero, so all chemical processes stop. So to understand what is going in xenon solution, we have to investigate the dependency of diffusion coefficients. Here you see the corresponding graphs. These two of them, light blue and violet, are for 5 and 4% of concentration. They are not of interest to us because at that concentrations we observe homogeneous nucleation of crystals, of hydrate crystals, which in this and at these temperatures. But in other three cases, from 3 to 1% of concentrations, we haven't observed neither crystal hydrate nucleations nor ice nucleation. And as you can see, the diffusion constant drops more than 10 times in this range. As you can see, the lowest temperature presented is 255 degree Kelvin, because at 250 degree Kelvin we couldn't observe any diffusion at all. So we tried to extrapolate this data to the area of lower temperatures. Here's the extrapolation. We used three coolest points, that is 255, 260, and 265 degree Kelvin, and extrapolated it, and the resulting parabola hit zero line at approximately 249 degree Kelvin. Just 1 degree from the temperature where we couldn't see any diffusion. It looks like this point corresponds to phase transition from azole phase to gel phase, that is to vitrification. And if yes, then the fourth possible mechanism can be marked as could be. And at such high temperatures, minus 25 degrees centigrade. If yes, then of course it's a kind of sensation, but you know our study is an simulation, and this result is extrapolation of simulation, so it needs experimental confirmation. So take-home message. Xenon may serve a cryoprotectant with several valuable features and no drawbacks at all. Well, except its high cost. Most interesting is its possible probability, ability to vitrify water at as high temperature as several tenths of centigrades below zero. It can be used with tolerable concentrations of common cryoprotectors because it is not easy to cool the body or an organ to even to several tenths of degree centigrade, but it's much easier than to cool it to liquid nitrogen temperatures. So we can apply reasonable concentrations of common cryoprotectors that are not so toxic in combination with xenon. And finally, we are open to any form of collaboration for investigation in this area. And we are going to go on with our studies. Here are the references. You can find them in the presentation file, which is available at this link. Thank you for your attention, and any questions?
Yes, let's start with Klaus.
What's the size of a xenon atom?
Xenon atom is about 2 angstroms.
Whatever. So I'm confused about your graphs of diffusion rates when you were showing towards the end of the talk. It seemed as though for 1%, 2%, and 3%, you had almost overlapping curves.
Yes, yes.
There. So what does that mean? Does that? I mean, it sounds like it doesn't matter how little you use, you still get vitrification at 248 or something like that.
You see, we are kind of confused ourselves because we thought that it's a kind of fluctuation, and we recalculated these graphs, and they were the same after recalculation, including, you see, this one where it's some kink, yes, and here you can see that at 4% diffusion rate is equal to 3% diffusion rate, and all that. So we don't know why these graphs behave this way, but this behavior was confirmed by a second computation.
And the second question refers to right near the beginning of your talk. You were talking about the advantages of xenon over
Yeah.
I don't understand why it would be advantageous in terms of rates of cooling and heating. You mentioned that.
You see, it easily penetrates tissues and cells, especially when we speak about cell membranes, which are a barrier for common cryoprotectants. The xenon atoms fluid through as if there are no cellular membranes, because it is lipid, and xenon is better soluble in lipids than in water. When you use xenon as an anesthetic, it's enough to make 1 or 2 breaths of xenon to sleep. And when you stop breathing xenon, then you make 1 or 2 breaths of air, and you awake in a good condition. And it can penetrate even through skin.
So why does that mean that you could cool more slowly or warm more slowly without crystallization?
I see. That doesn't mean that you can cool more slowly, but if you have to cool to, say, 25 degrees centigrade, it's much easier than to cool to 130 degrees centigrade.
If the solubility is low at room temperature, how do you get the sufficient xenon into an organ like the brain?
At what temperature?
The solubility, I thought you said, was very low at room temperature.
Yes. It's, as I've said, xenon is a mystical substance, and we don't know what is the mechanism behind its anesthetic action. So a very low concentration of xenon makes you sleep.
What is the concentration that makes you sleep? Anywhere near?
You see, I do not think that anybody have measured the concentration in human brain, but the mixture that is used for anesthesia is 20% of oxygen and 80% of xenon, or enough 70% of xenon and 30% of other. 75, 70, 75, 80.
Yes, did you perform any calculation what would be the cost for the human preservation using xenon?
No, we hadn't calculated the cost, but it's several decades ago, I found the fact that a kilogram of xenon costs approximately the same as a kilogram of gold.
But how much xenon we need?
I don't know what are current costs of gold or xenon.
Doesn't matter, but how much xenon we need now?
If you need, say, 1% of water concentration of xenon, there are maybe 50 liters of water in the body, so about half a kilogram of xenon.
Okay.
I'm not sure that it is as costly as gold now, currently, because it was several decades ago, but I think the order of magnitude is the same.
Okay. One final question? None? So let's thank the speaker again.